Our second shuffle is a judicious transpose in which the stacking is just slightly different from that of shuffle 25. But look how different the cycle notation of the permutation is. So let's go ahead and derive this permutation. So we begin with our ordered packet 1 through 8 and we perform the shuffle. So as always, we're just dealing out pairs 1, 2, 1, 2, 1, 2, 1, 2. The stacking is as follows. 4 gets stacked on top of 2. 3 gets stacked on top of 1. And now this time we will stack the left pile on top of the right, unlike the previous shuffle where we stacked the right on top of the left. We also refer to this as a leapfrog stacking because we're jumping over the neighbor to the left. So what ordering of the cards do we obtain? After completing that shuffle, we get 6, 5, 2, 1, 8, 7, 4, 3. Expressing this in Cauchy's two-line notation, we obtain the following. The second row here is 6, 5, 2, 1, 8, 7, 4, 3. Converting this to cycle notation, we obtain the following. 1 goes to 6, so we have an arrow from 1 to 6. 6 goes to 7, an arrow from 6 to 7. 7 goes to 4, an arrow from 7 to 4. And then 4 cycles back around to 1. So that completes this 4 cycle. For the remaining values, we obtain the following. 2 goes to 5, so we have an arrow from 2 to 5. 5 goes to 8, so there we go. 8 goes to 3, and then 3 cycles back around to 2, completing a second 4 cycle. Color coding our digits, we obtain the following. Recall that position values 1, 4, 6, 7 are color-coded black, and position values 2, 3, 5, 8 are color-coded red. This will help us determine whether there's been a preservation of the cards that started in these positions, ending in these positions, the same thing here, or if there's been a wholesale replacement where cards that originally began in positions 1, 4, 6, 7 get moved to positions 2, 3, 5, 8 in some assignment. And those two outcomes are represented here below. So we see that black 1 goes to black 6, which goes to black 7, which goes to black 4, which cycles around to black 1. Red 2 goes to red 5, which goes to red 8, which goes to red 3, which cycles around to red 2. So we see that each value gets sent to a value of the same color. So inversion does not occur here. All of the cards that began in one of these position values gets moved to one of these position values. The same thing here. Cards that began in any of these positions will stay within that list of position values. Now, it is true here that we're looking at a shuffle of order 4. So it will take 4 applications of this shuffle to return the packet to its original order. Now that's in contrast to the one that we just did, shuffle 25, where this is a shuffle of order 2. Performing that shuffle just twice resets the packet to its original order. Now let's go ahead and show the effect of this shuffle on the Bessey sequence 1001. 0110. And according to what we've just shown here, we should get this exact form back once the shuffle is complete. So let's go ahead and perform it again. So you deal out into piles 1, 2, 1, 2, 1, 2, 1, 2. And the stacking is this leapfrog stacking. The fourth pile leaps over the third, lands on top of the second. The third pile leaps over the original pile 2 onto pile 1. And now we're stacking left on right. So it should be the case that we get 1, 0, 0, 1, 0, 1, 1, 0. So we have preserved the Bessey sequence form, even though the actual cards themselves have been permuted. They have moved around. In fact, they've moved around in the way described right here in cycle notation, or if you would like, as described here in Cauchy's two-line notation. So every single card is being moved to a different location than where it started. And taking a look at the Bessey shuffle diagram, recall 1 goes to 6, which goes to 7, which goes to 4, which goes back to 1. Let's check that. 1 goes down to 6, and then up to 7, and then down here to 4, and then straight up to 1, completing that cycle. We also say that the values 1, 4, 6, 7 constitute an orbit, since they are simply moved around among themselves. Here we know that 2 goes to 5, which goes to 8, which goes to 3, which wraps around to 2. So let's check that. 2 goes to 5, 5 goes straight up to 8, 8 goes down here to 3, and then 3 goes straight up to 2, completing that 4th cycle. Also showing that our second orbit consists of 2, 3, 5, 8. And here we've indicated that inversion has not occurred. Also, please note that this shuffle here is actually the inverse of one of the shuffles that we looked at in our last video, video 6 in this series. So why don't we go ahead and take a moment and discuss that. So here is shuffle 24, video 6 in this series. And if you look at the diagrams themselves, the diagram for shuffle 26 right here, top row right, and the diagram here, bottom row right, you'll see that the diagrams themselves are identical except for one important difference. All of the arrows have been reversed. So for instance, over here, 5 goes up to 8, but for shuffle 24, 8 goes down to 5. So these two shuffles undo the effect of the other. So performing these two shuffles in succession will give you the identity permutation. Now, in some ways, this isn't obvious that these should be inverses, actually. Just look at how the stacking is done. It would actually take a fair amount of detective work to deduce that these would even be inverses. So here we have our packet 1 through 8. So why don't we go ahead and perform our new shuffle, shuffle 26 right here. And then we'll follow it up with performing shuffle 24. And see if you can follow what's happening with the cards and readily detect that these really would undo each other. Okay, so shuffle 26. What do we do here? We deal into pairs, as always. 1, 2, 1, 2. And for shuffle 26, the stacking is from right to left in this leapfrog stacking. You're leaping over its neighbor. So 4 goes on 2, 3 goes on 1, and then in shuffle 26, we stack left on top of right. So we're going to go like this. Okay, so just think about the new ordering of the cards. In fact, we can show you the new ordering. Of course, it will be a mess. 6, 5, 2, 1, 8, 7, 4, 3. Okay? Now let's go ahead and follow that up with shuffle 24 from last time, because according to the shuffle diagram, this shuffle should return this packet to its original order of ace through ace. So let's go ahead and perform this one. So it begins the same, but dealing into pairs. But the stacking this time is pile 1 gets stacked on top of pile 3, so it's a leapfrog stacking, but it's from left to right. Pile 2 gets stacked on top of pile 4, and now we stack the right pile on top of the left. Now apparently the packet should be back to its original order, which it is. So I don't know if anyone, especially on the fly, would be able to detect that shuffle 24 and shuffle 26 undo each other. So in particular, what that would mean is you could perform shuffle 24 and shuffle 26 as many times as you like and in any order, as long as the number of times you've performed shuffle 24 is the same as the number of times you've performed shuffle 26. So for example, you could perform shuffle 24 twice, and then shuffle 26 once, and then shuffle 24 once, and then shuffle 26 twice. And we will have performed each shuffle a total of 3 times, which guarantees that we will return the packet to its original order. So try that out. Perform shuffles 24 and 26 the same number of times, but in different orders, and see what you get.